If you need to know the exact thickness of a single guitar string or the diameter of a thin copper wire, you run into a physical limitation very quickly. A standard ruler relies on the human eye to estimate fractions of a millimeter. When the object you're measuring is smaller than the smallest line on the scale, that estimate becomes a guess. A vernier caliper helps by bringing the resolution down to 0.1 millimeters. But in high-precision manufacturing, even that tenth of a millimeter is a massive, unacceptable margin of error. Moving from general construction to the microscopic tolerances of micromanufacturing requires a leap in resolution. To work at the scale of 10 microns, we have to look past the sliding scale and toward the mechanics of a screw. This is the micrometer screw gauge. It features a rigid U-shaped frame, a fixed anvil, and a movable spindle. Instead of a sliding jaw, the handle, or thimble, is covered in vertical and horizontal lines corresponding to the rotation of an internal screw. To take a measurement, we have to understand the specific relationship between how far we turn this handle and how far the spindle actually moves. Once we understand that ratio, we can translate mechanical rotation into a precise linear distance. The secret is the pitch. Inside the tool is a precision screw. For every full 360-degree rotation of the thimble, the spindle moves forward by exactly 0.5 millimeters. You start by placing your object between the anvil and the spindle and rotating the handle to close the gap. But you shouldn't tighten it by the thimble alone. To get an accurate reading, you use the ratchet at the very end of the handle. You rotate the ratchet until you hear a clear click. This indicates the spindle has applied uniform pressure and stopped moving. This uniform pressure is vital. By ensuring the tool grips every object with the exact same force, we eliminate the variations that would otherwise ruin our mathematical precision. Reading the result is an additive process. We start on the stationary sleeve, looking at the main scale. On this specific scale, we see the number 2 is visible. This gives us our primary reading of 0.200 inches. We also see one small vertical line past the 2. Each of these subdivisions represents 0.025 inches, which we add to our total. For the final microscopic fraction, we look at the rotating thimble. This is where we see the least count, the smallest increment the tool can detect. We find the mark on the thimble that aligns perfectly with the sleeve center line. In this case, it's the number 1, which represents 0.001 inches. By adding these three values together, 0.200, 0.025, and 0.001, we reach a final measurement of exactly 0.226 inches. The micrometer essentially breaks a single measurement into layers, stacking different scales to reach a level of accuracy that a simple ruler cannot achieve. However, even a precision tool can be misleading. If you close the gauge completely and the thimble 0 mark doesn't align with the sleeve's baseline, the tool has a 0 error. A positive error occurs when the thimble 0 mark stops below the reference line. Because the tool is starting ahead of 0, we have to subtract this error from our final result. A negative error is the opposite. The 0 mark sits above the line. This means the tool is underreporting the distance, so we must add that error back to our measurement to find the truth. Accuracy isn't just about having a high-resolution tool. It's about identifying these mechanical offsets and correcting the math before recording the data. With that final correction, we can say with mathematical certainty exactly how thick our object is, down to the last thousandth of an inch. In an industrial setting, this precision is what allows parts from different factories to be interchangeable. It ensures that a bearing fits perfectly into a housing, or that a wire has the exact diameter needed for a specific electrical resistance. Without the ability to standardize measurements at this scale, mass production of complex machinery would be impossible. Parts would simply fail to fit together. True precision isn't found in a perfect instrument. It's found in the process of understanding a tool's mechanics, accounting for its flaws, and letting the math lead you to the correct result.